How's it going, everybody? Today I'm going to introduce Chapter 6, and I'm going to step back from using the slides. I'm actually going to focus primarily on my notes here, and we're going to go through it. I actually was going to write this out as I did it, and I did record it that way, but then I deleted the video by accident. So I'm just going to run through my notes right now, and then we'll answer any questions you have later. So I'm going to cover 6.1 and 6.2, and hopefully 6.3. in this presentation. So first, Chapter 6 covers the sample distribution. And 6.1 specifically follows the mean and the standard deviation of the sample. Okay, so I want to talk about the sample right now, and I want to define a couple of variables that we're going to use here. This cursive little x, see the tail here? Notice the difference between this x and this x. This x represents the sample mean, has a bar over it. And it varies from sample to sample. So it's not always going to be the same based off of the sample that you have. You're going to have different means. Are they going to be close to each other? Potentially. But they're going to be different based off of the sample. And obviously there's going to be a specific sample size that you would hope would be consistent. But these sample means will be different. And it cannot be predicted with certainty. So we have, we can't say for sure a sample mean is going to be this. We can, we can take a guess and say based off of these tests that this is what it was, but we can't predict it with certainty. The other one is this, the random variable. So this is a solid, a straight X here with a line over it, a capital X with that matter, and this represents a numerical quantity generated by a random experiment. So when you generate a random experiment, you're going to get a value, and that represents this value right here. And then from this, we can say that because we are dealing with a random variable, the mean of the random variable is represented like this, or the sample, right? The standard deviation of the sample, right, would be written like this, okay? And there's one formula in particular here, but basically the mean of the sample is, we just call it the mean. It's pretty straightforward. The mean of the sample is the mean. And then the standard deviation of the sample happens to be the standard deviation divided by the square root of your sample size, random sample being n. So when we talk about, how many people are in our collection, that would be your value. How many people am I testing in an experiment, or how many plants am I testing? That would be your value of n there. Okay, so we're going to take a look at an example right now. This example talks about the tax value of a vehicle registered in a particular state. We do not know what that state is, but particular state. So the tax value of a vehicle registered in a particular state, it has a mean of 13,525, and it has a standard deviation of 4,180. So basically what we're going to do is we want to figure out what the standard deviation of the random sample is. What is the standard deviation of the random sample? And the sample size that we're working with is 100. So we have 100 people, or 100 values, vehicles registered in a particular state, and we want to know what are the tax, the tax value of those vehicles in a particular state. Okay? So basically what we have here is we can call this the mean of our sample. All right, this is the mean of our sample, and we're calculating the standard deviation of our sample. So since our standard deviation of the big picture here is 4,180, we can divide that by the square root of 100, 100 being the random sample. When we divide it out, we can say that the standard deviation of our sample is $418. One very, very important piece that I'm going to mention here, and I'm going to repeat on the next side of notes here, is that as the sample size grows, the standard deviation decreases. So I want you to think about that. If we were to expand this number, say it became 225. I chose 225 because it's a perfect square, right? But the square root of 225 is 15. And so 15 is obviously larger than 10. So if I'm going to divide 4,180 by either 10 or 15, obviously the value over here is going to be smaller if it's divided by 15. So as my sample size grows, the standard deviation is going to decrease. Okay. Now at this time we're going to take a look at 6.2, and 6.2 talks about the sampling distribution. of the sample mean. And first thing I want to cover is just the central limit theorem. So, and basically the central limit theorem has to do with the sample size. If n is a value that is greater than or equal to 30, then the mean is approximately normal. And so what do we mean by the mean being approximately normal? What do we mean by something being normal? We're going to talk about it down here when we talk about normal distribution. This is just a little bit of a review from chapter 2. But I just want to reiterate these two formulas that we used, and I also want to reiterate the larger the sample size, the better the approximation. That's something that we're going to carry with us and use over and over again in this class. Remember, this represents the standard deviation of the sample. The standard deviation of the sample, where sigma alone just simply represents the standard deviation in general. Okay? So now if we take a look at a bell curve, so what makes data normally distributed? So there's three things that have to fall true in order for us to say that data is normally distributed. Basically, if we know what the mean is, and we know what the standard deviation is, if we subtract one standard deviation from the mean and add one standard deviation from the mean, then we can say that there is going to be approximately 68% of the data in between one standard deviation of the mean. Likewise, if we subtract two standard deviations from the mean and add two standard deviations from the mean, we can say that there is approximately 95% of the data between two standard deviations of the mean. And additionally, for three standard deviations of the mean, if we add three standard deviations or subtract three standard deviations from the mean, we can say that just about almost 100% of our data, not quite, but 99.7% of our data lies between three standard deviations from the mean. So this is something that's important as well. This is one of those things that you're going to want to maybe cut, paste, copy, put in, and you can do that right from the slide presentation. There is all that information right there for you to take a